All right, so let's start by talking about point estimators, confidence intervals, and the t-distribution. So we're moving now into a new area of statistics, the area of inferential statistics, and we're using data from samples to estimate the values of unknown parameters in populations. And so inferential statistics is this process of using data from samples to draw conclusions about populations. So I want to start by defining some terms, and the first thing to start with is what's referred to as an estimator, and this is a random variable or a sample statistic that's used to estimate an unknown population parameter. And so the actual numerical value that's obtained for an estimator is usually called a point estimate. And and again, an estimator is a statistic that's a measure from a sample. And so the most common estimator, the one we're going to talk about the most, is the sample mean, often referred to as using the symbol X bar. And so this is an estimator of the population mean, often signified by the Greek letter mu. Also, the sample variance, which is S squared, that's how it's often signified, is an estimator of the population variance, sigma squared. So those are two common estimators we're going to be talking about. Confidence intervals, so what a confidence interval does is provide us with a probability range for our estimator. And so this is the range within which we would expect a true population value, such as the mean, to lie. And so we make a point estimate from the sample, but we know if we sampled again, we'd get another value. So, you know, the value of the estimator is somewhat dependent on the sample, and you're going to randomly sample different people out of the population, so you may end up with different point estimates. So this is why we use the confidence interval, because it gives us a range or margin of error on our point estimate. And what it does is provide an interval with an upper and lower limit on our mean, and gives us a probability that our estimator lies within that range. So typically we would use 95% confidence intervals, which would mean we're 95% certain that the population mean lies somewhere in that range. And so the confidence limit is, the limits are the left and right hand, the lower and upper bounds on our confidence interval. So if we just want to talk about the general form of a confidence interval, we're talking about the point estimate plus or minus some test statistic multiplied by the standard error. And so we're going to be spending a lot of time in the next couple lectures talking about these different forms of test statistics. And we've already talked about the standard error earlier in the course. And so the test statistic is the value of the relevant statistic necessary to get the desired range of values, percentage range of values, typically 95% of values within that range. And so for the normal distribution in a large sample, to get 95% of the values around our mean, X bar, the statistic we would use is the Z statistic that we talked about in the previous lecture. And the value, if you look it up in your table and we're just interested in the 95% confidence interval, the actual value of the Z statistic is 1.96. Okay, so let's talk about confidence interval for a normally distributed mean with known variance. So first, the assumptions, the things that we're assuming in order to do this, are that our population that we're sampling from is normally distributed, or based on the central limit theorem, as long as it has a sample size of 30 or greater, then we can assume our sample is normally distributed. And we're also assuming that the population variance sigma squared is known. And so the formula for calculating the left hand and the right hand side of the interval, so the lower and upper side, our sample mean X bar, subtract whatever Z statistic we're interested in for a given level of alpha. If we're interested in alpha of 0.05, whatever that given level of alpha is on the left-hand side, whatever the z statistic value is, and then multiplied by the population standard deviation divided by the square root of n, which is the sample size. So what's important there in that these two formulas for the left and right hand side, you'll notice that the only difference is that on the left hand side we're subtracting whatever the value of z is, and on the right hand side we're adding it. And so if we're interested in a 95% confidence interval, the value of alpha that we're interested in is 0.05. And so I put this step-by-step recipe for calculating the confidence interval below, and I'm also going to post a Word document on Blackboard that's going to contain a number of these step-by-step recipes for you to use. So the first step is we choose the desired value of alpha. Normally that's going to be 0.05. And the next step after that is finding the z-score in the z-table, and that table's in the appendix in your textbook, corresponding to z, and then the subscript there is alpha divided by 2. So the z-score is for the left and the right tails of the distribution, if you'll remember. And so an alpha score of 0.05, meaning we want to include the central 95% of observations, but exclude 5% of the observations. We actually want to divide that alpha by 2, because then we get 2.5% of the observations in the right tail and 2.5% of the observations in the left tail. And so in order to calculate this, you find the z-score at 0.50 and you subtract 0.025 from it. And so the probability there is 0.475. So you want to find the z-score that corresponds to a probability of 0.475, because that is the amount of the probability that you want to include on either side of the mean. And that z-score is equal to 1.96. And so it's called plus or minus 1.96 there, because if you plug it in to the right-hand side of the formula there, you're adding it, but on the left-hand side of the formula, you're subtracting it. And so what you want to do, the next steps in the recipe are you want to identify the other parts of the equation. So that's the sample mean x bar, the population standard deviation sigma, and if you're given the variance instead sigma squared, then you would just take the square root of it, and then also n, which is the sample size. Then you have all those values and you can compute and plug them in on the left and the right hand side of the equation there to get the confidence intervals. And so let's walk through an example. Hopefully it'll make it a little bit clearer. So again, we're looking for the 95% confidence interval for normal mean and known variance. We have a sample of 10 patients. Say they're given a drug to improve their sleep, and the mean improvement in their sleep time was 65 minutes. Let's say we also know that this population is normally distributed with a standard deviation of 1.7 minutes. And so you can see I've put the formulas there for computing the left and right hand side. So to compute the left hand side, we take our mean of sample mean is 65, and then we subtract the z-score of 1.96, because that's the z-score that corresponds to an alpha equal to 0.05, and remember that's the two-sided alpha, so we're actually looking for 0.025 on the left, 0.025 on the right, and that's the two-sided alpha value, that value of 1.96, that's the z-score. You multiply that by the population standard deviation over the square root of the sample size, and the result for your left-hand value is 63.9. You go through those exact same steps for the right-hand side, the only difference being you're adding the z-score of 1.96 multiplied by the standard deviation divided by the square root of the variance. You get an answer of 66.1. So we can say that we're 95% confident that the drug increased sleep time somewhere between 63.9 to 66.1 minutes. And so we have our mean lies in the middle of that distribution. Okay, so the question you might have is, well, what if we don't know sigma, the population standard deviation? And so if it's unknown, and I kind of hinted at this in the last lecture for Module 7, we estimate the population standard deviation using the sample standard deviation S. And so when S is used, the sampling distribution of the mean no longer follows a Z distribution. It follows a T distribution instead. And it's a T distribution of the standard normal distribution. And so the T-score is computed a little differently than the Z-score, but not that much differently. The T-score is equal to the sample mean minus the population mean divided by the sample standard deviation, which is then also divided by the square root of the sample size n. And so, interestingly enough, the t-distribution, also referred to as the student's t-distribution, this methodology was originally developed because employees at Guinness had a question about how many samples of beer must be taken to be reasonably certain that the beer is safe and tasty, something that I know is of great concern to all of us. And so the employee at Guinness working on this problem discovered the family of t-distributions and published it anonymously as student. So we should be thankful to Guinness, I guess, for more than one reason. All right, so moving on. So the t-distribution is shaped like the normal distribution, but it doesn't assume an infinite number of observations like the normal distribution does. There's a family of t-distributions, each with the same general shape, but varying slightly in the tails with sample size. So the smaller the sample, the heavier the tails of the distribution gets. As the sample size becomes larger and larger, though, the t-distribution more and more approximates the normal distribution. And so here's an exhibit where you can kind of see how it looks like. So the normal distribution is in black, if you can see that, and then as the sample size decreases, you go down to red, to blue, to purple, you can see that you're seeing on the t-distribution less and less area under the center and more under the tails. But the t-distribution really is very similar to the normal z distribution. Okay, so some assumptions for using the t-distribution. We're assuming normality in the population, that the population we're sampling from is normally distributed. Or under the central limit theorem, we can just assume that if our sample size is greater than or equal to 30. So we would use, if we were to use the t-distribution with observations that are not normally distributed and or when the sample size is lower than 30, this could lead to inappropriate confidence intervals that are narrower than what reality actually would be. Okay, so we're going to talk now about the sample variance and also degrees of freedom under the t-distribution. If you remember, when you learned to calculate the variance of a sample population, you already learned this formula a few lectures ago. And so this is simply, if you remember, we're taking each individual observation and subtracting the mean from it and then squaring that. Also called the sum of squares, dividing it by the sample size minus 1. And that sample size minus 1 also is the degrees of freedom. We don't need to go into all the mathematical reasons for that, but an estimate was made that, so the sample mean is a good estimate of the population mean. And so that's like considered one restriction, statistically speaking. And so that means that we have one less degree of freedom than the number of independent observations that were made, etc. Okay, so let's talk about the confidence intervals and get into how we actually compute these using the t-distribution. So we're talking now about confidence intervals for normal means and unknown variance. So this is very similar as to when we're using the z-distribution. As you can see in the formula there, whether we're looking at the left or right-hand side, we start with the sample mean x bar. Instead of subtracting a z statistic, though, we're subtracting the t statistic. Again, that t statistic is based on the value of alpha we choose divided by 2 because we're interested in both tails of the distribution, and then the degrees of freedom, which are equal to n minus 1. And when you look up the critical value in the t table, it's important that you know the degrees of freedom. So that t statistic is then multiplied by the sample standard deviation divided by the square root of n, which is the sample size. The right-hand side is the exact same formula, except you're adding the t score instead of subtracting it. So if we were to go through a step-by-step recipe, again, I've posted this online. The first step is to choose your desired value of alpha. Typically, that's going to be alpha 0.05, which implies a 95% confidence interval. Then you want to identify your sample mean, your sample standard deviation, and n, the sample size. Compute the degrees of freedom equal to n minus 1. And then you want to find the t-score in the t-distribution table. And this table is in the appendix in your textbook. And so this is the t-score corresponding to t with a certain alpha value, in this case 0.05, divided by 2 for n minus 1 degrees of freedom. So this is the t-score for the left and right tails of the distribution. If alpha equals 0.05, then look up the t-score listed under 95% in the table in your textbook for the t-scores. And you also want to look up the two-sided t-score in the appropriate column. So there's a place to look up a one-sided t-score and a place to look up the two-sided t-score. If we're talking about confidence intervals, you want to look up the two-sided t-score under 95% in the table. Then you also, so that's going to be in the appropriate column. On the rows along the far left-hand side, you'll see degrees of freedom. So you want to use the row corresponding to your degrees of freedom. You triangulate those, and it'll give you the t-score. And then you simply plug that t-score into the formulas for the left and right side of the confidence interval, and you have your confidence interval. So if we walk through an example, let's say we had a sample of 10 U.S. states. And let's say previously we knew that the mean percentage of obese adults was 28.1. We also know the population for BMI is typically normally distributed, and our sample standard deviation is 3.5. So you can see, again, I put the formula up for calculating the left and right-hand side of the confidence interval. The left-hand side is equal to our mean of 28.1 minus our t-score of 2.262. So how did I get that t-score? I simply looked up the t-statistic that's in the t-table in your textbook for 95% for the two-sided t-score for a degrees of freedom of 9, because it's the sample size 10 minus 1, and that gives a t-score of 2.262. So that's multiplied by the sample standard deviation of 3.5 over the square root of the sample size of 10 gives a result of 25.6, and that's the left-hand side of the confidence interval. The right-hand side of the confidence interval, we use the same formula, except we're adding 2.262 multiplied by 3.5 over the square root of 10, and that gives us 30.6. And so now we can say that we're 95% confident that the U.S. population mean obesity percentage lies somewhere between 25.6 and 30.6.